speaker is Stjepan. He's going to talk about reverse engineering of neural network architecture via sidechannel. He's an assistant professor at TU Delft and also the chair for Eurocrypt conference this year. From my personal interaction with Stjepan, he's a big time collector of handmade watches and knives. When I heard that he's a collector of knives, it freaked me out, but I know he has this tool in his house that you can actually make knives out of. So yeah, Stjepan, the stage is yours now.
Okay, cool. So hello everyone. Yes, thank you for a very nice introduction. You could have skipped the part with knives, but okay. So yeah, today I will be talking about reverse engineering neural network architectures through EM side channels. So this is a joint work with Leila Batina, Shivam Basin, and Dirman Toyab. So let's go immediately into the material. So basically, machine learning is everywhere. So various industries, various domains use machine learning for various applications. And actually, we do see the same stuff happening in security domain. So many security applications today rely either as a main tool or as a helper tool on machine learning. And then in that kind of setting, we can say that actually having strong machine learning models is actually an asset. So it's a value. So if you have a task and you have very good machine learning model to solve that task, it's not, maybe this kind of information you don't want to share with your competitor because you spent a lot of time, a lot of money, a lot of manpower to make a model like that. And then the question is, okay, you have that model. You think now you have something that you can use and your competitors do not have. But how secure are those models against reverse engineering attacks? And immediately I must say, this is nothing new. So people are actually investigating how the leakage of sensitive information from machine learning model is happening. So it's a well-known topic and people are exploring it from various perspectives. Usually they explore it from perspective of using some kind of specific thing, something special. For instance, you use a special kind of implementation of your neural network, and simply because it's implemented in exactly that way, you can use, for instance, timing or memory leakage to break it. For instance, you could exploit line buffers in convolutional layers of CNNs, convolutional neural networks, and similar. But main message is you use something specific, so something implementation specific to do your attack. What do we do? Well, what did we ask the question? We asked the question, can we again use the same kind of attack, so use the side channel information, but try to be as generic as possible. So recover neural network architecture using only side channel information. We do not make any assumptions on the inputs or source because we work with real numbers. So that makes it very nice for us. Whatever kind of values, it will be covered basically with real numbers. The main assumption we do make is we assume that the implementation of machine learning algorithms do not include any side channel countermeasures. And now one can say, wait, this is a huge assumption. But currently it's still actually not, because if you would be looking at real world applications of machine learning, most of them all, as far as I know, basically everyone in a realistic application will not be protected against side channel because simply the attack is relatively new, the domain is new, and there is a cost if you wanna protect. You will pay implementation cost. So either you will spend more power for your algorithm or you will need more area to add countermeasures and so on and so on. So what do we do? Our attacker is a passive one, which means the attacker can only listen. He will not change anything. He will acquire measurements of the device and that device operates normally. So he will not do any kind of fault injections, so nothing that will go into the domain of active attacks. And of course, attacker does not know the architecture of the used neural network, but he can feed random inputs to the architecture. So this is very important point. he needs to be able to feed known inputs to the architecture. And of course, since we are doing side-channel attack, the attacker must be able to measure side-channel information leaked from the implementation. So here we played with Atmel, Atmega, and ARM Cortex chips. Why? Because we were saying, well, we are interested in embedded devices, in devices that one could find in actuators, in sensors in real world. And these are kinds of devices that one would really observe in settings like that. So I'm not sure how many of you know about side-channel attacks, about implementation attacks. So let me just give 2 slides of quick introduction. What are side-channel attacks? What are implementation attacks? Implementation attacks are all those attacks that do not aim at the weakness of the algorithm, but on the implementation. And there, side-channel attacks are passive, non-invasive. And actually, they are very powerful, and usually they are considered in the domain of cryptographic devices, and they are considered as one of the most powerful categories of attacks. But we will see they can be used outside of crypto, like in this application today. So we are attacking neural networks, nothing cryptographic there. And side-channel analysis, of course, have many, many techniques that one can use. I will only mention differential power analysis, commonly known as DPA, or differential electromagnetic analysis, commonly known as DEMA, though they are, let's say, advanced forms of side channels, and they apply statistical techniques to recover secret information. So let me show immediately on the scheme how it looks like. So this would be a scheme of differential power analysis. You have your input. On one side, you have your real information, real measurements. On the other side, you have your model, your hypothesis. Basically, you compare the real one with the hypothetical one. You do some kind of statistical analysis, and where your hypothesis fits the best, you say, well, for this case, my hypothesis is correct. Of course, see the feedback loop. It means you need to check every possible hypothesis. So something connected with the previous talk, our setup is microcontrollers or ARM chips. We do use acid to decapsulate the chips. And here on the left side, you can see how the chip looks like when it's decapsulated. I must tell you, the decapsulation is not really necessary. It would work without it, but when you do decapsulation, you get much cleaner signal. And on the right-hand side, you see the Langer EM probe, which we use to do the measurements. And this is the whole setup. So you can see there is a fancy oscilloscope, there is the probe, there is the chip, and one does the measurement. And I will also mention something that John said in the previous talk, when he was saying that there are other types of attacks, do other stuff before going into this because it's complicated. The same is valid here. If you can do simpler attack to recover the architecture, maybe that is a good way, because what we do is a generic attack, is a powerful attack, but it is not really a simple one. So how do we do the attack? Well, we exploit the leakage of the target device. And the common leakage is the Hammingweight model. So why? What does it happen? Well, microcontroller loads sensitive data to a data bus and performs any kind of instruction. So basically we have the correlation, how many bits do change, what is the Hammingweight, we see some change in the power or electromagnetic radiation. Training phase for neural networks is of course done offline, so regardless of what we are doing, and the training network is basically implemented in C and compiled on the microcontroller. So I already said the goal is to recover neural network architectures. But what kind of neural networks are we talking about, and what does it mean architecture? So here we talk only about feed-forward neural networks. Why? Because they are the most popular ones and most used ones. So those would be something like multilayer perceptrons or convolutional neural networks. And what do we actually do? So we recover information about layers, information about neurons, information about activation functions, and information about weights. So every possible weight of every neuron can be recovered in this way. So what's activation function? Well, it's a function defining the output of a node given an input or set of inputs. Here I write 4 commonly used activation functions: sigmoid, tanh, softmax, and relu. There are tons of activation functions. So you can go on Wikipedia, I think there would be listed 20, 30 at least. This procedure can be done for any activation function, but these are commonly used, so this is why we do it. I give here equations for those activation functions. You do not really need to go into details, or you don't even need to understand those equations at this point. What's important to notice immediately is that the equations are very different. So for instance, if you check the first one, f of x is equal 1 divided by 1 plus a to the minus x. And the last one, f of x is max of 0 and x. You can see they are very different. So what can we immediately deduce from this? Well, if we check the timing characteristics of those activation functions, we should expect quite different behavior. And actually, this is what happens. So here I give some numbers. So for each activation function, what's the minimum, maximum, mean time, computation time. But much more interesting will be the graphs. So you can see here the behavior of each activation function. And indeed, relu, sigmoid, tanh, softmax, they look very different. So with this, we can already say, well, simple timing attack, we can deduce what kind of activation function one uses. Let's go next. So what did we say? We said we need activation functions. We need the weights. Well, how do we recover the weights? I think this is the coolest part of the procedure. So we simply use the correlation power analysis, CPA. That's a variant of DPA, the graph I showed you a couple of slides ago. The only difference is here for the statistical technique, we use Pearson correlation. So how does it work? Well, we will target the multiplication operation. So M is equal X times W. So X is the input. Remember, we know the input, and we want to get the secret weight W. Then using the Hammingweight model, the adversary will correlate the activity of the predicted output for all hypotheses of the weight. So he will calculate all hypotheses, and then the correct value of the weight will hopefully result in a higher correlation, and it will basically stand out among all wrong hypotheses. We will see later how it really looks like. But just a little bit more technical details how to really do it, because when I say, well, we just correlate, we multiply, it sounds simple, but there is a little bit more. So first, let's analyze how does the compiler handle floating point operations. Well, it will use the standard IEEE 754, and then since our target is 8-bit microcontroller, it will follow 32-bit pattern. So it will use 4 registers to store values. And then, of course, those 32 bits will have the sign bit, the biased exponent bits, and mantissa bits. So target the result of multiplication, known input, unknown weight. For every input, we assume different possibilities for weights. We perform multiplication, estimate the binary representation. We do that for mantissa, we do that for sign and exponent separately, and this is how it looks like. So the black line is the targeted value, the red line is the incorrect value. So the black line is what you get when you have the correct hypothesis. The red lines are for the wrong hypothesis. So on the left side, you see the picture for the first byte recovery, on the right side for the second byte recovery. So what can we see here? It works. We can definitely see the difference between the black line and the red line. But if we check the numbers, actually the difference is not so big. So one would say 0.85, 0.9, it's not big difference. Yes, but in sidechannel, actually this kind of difference is quite significant. So with this, we can get what is the weight of every neuron. So there is a lot of work to do that, many neurons, so many experiments, but we can get what's the weight of every neuron. What kind of precision can we get? Well, depending on the representation, how many values are we willing to test, how many hypotheses do we want to have. The more precision, the more hypotheses we need to test. So here we go up to 2 decimal places of precision. Cool. So now we have the activation functions and we have the weights. What is left? Well, we need to get what's the number of neurons, what's the number of layers. And actually, to get the general structure, we can do very simple attack called simple power analysis or simple EM analysis, which is basically done by visual observation. So check here 3 different pictures. So first one is a very simple neural network, 1 hidden layer, 6 neurons. Then picture B is 2 hidden layers, 6 and 5 neurons. And 3 hidden layers, 6, 5, 5 neurons. So what we can see, well, we can actually recognize patterns. At this point, forget about these red lines. These red lines look as magic, because one could say, well, for the first picture, it's clear. I just separate the neurons. But how would I know for the second picture that exactly here is the boundary between the first hidden layer and the second hidden layer? So let's forget that and leave that for next slide. What's important message here is even by simple visual observation, we can see what's the number of neurons. Okay, so now we have 3 out of 4 things. The only thing we need to do is recognize how do we say when is the boundary of one hidden layer and where does the second or third or any hidden layer begins. How do we do that? Well, actually, not so difficult. We use the same concept as before, and we just do weight recovery by using 2 sets of data. So I will explain now how it would work if we would attack the first hidden layer, but this approach works for every layer. So we have the input, vector of length and 0, and remember we know the input. And then for the targeted neuron in the hidden layer, we perform the weight recovery with 2 different hypotheses, okay? This is the important part, 2 different hypotheses. The first one, we assume that neuron is in the first layer, in the first hidden layer. And we do our weight recovery with that assumption. And then we do the second assumption that says, no, that neuron is in the second hidden layer. Because let's agree, if we aim a neuron, it needs to be either in that layer or in the second one. And again, we repeat the experiments, we do the weights recovery, and then we record the maximum correlation value and compare. And one of those hypotheses will have the higher correlation, and it will tell us if our first hypothesis was correct, so it was first layer, or our second hypothesis was correct, it was second layer. And then we know what's the boundary, because we start with the first neuron, go, we reach the boundary, we know, okay, this is the boundary, now it's the second layer. We repeat, boundary, third layer. Continue. So to recover the full network layout, you need to combine all those steps. So timing for activation functions, simple power analysis for the neurons, correlation EM analysis for the weights, for the layers. And this is how it looks like in the whole framework. So first you do your acquisition, you collect your timing information, your power information, your EM. Then you perform your CPA to obtain 2 weight candidates. You compare, you find the layers, you identify the activation functions, and you reconstruct the network. Sounds simple. So what kind of result can you actually get with this? By the way, I say sounds simple, but actually with the number of experiments one needs to do, it's quite complicated and long process depending on the size of the network. But what can we do? Well, first, this is how it looks like when we do something more realistic. So ARM Cortex-M3. This is multilayer perceptron, and we can already see here that sigmoid and tan H look quite similar, much more similar than before. But actually, the values on the y-axis are different. So while the patterns look the same, the values are different. So it's easily still recognizable what kind of activation function do you use. And these are how would you see the patterns of the timing and the correlation. And here actually you can see what does it mean to have small differences between your correct hypothesis and everything wrong. But even this, of course, is enough if you use enough traces. So what can we see here on picture B? So you can see already if we have around 500 traces, we can see good distinction between black and red line. And of course, the C picture just depicts hidden layers neurons. So now I told you, well, we can recover the neural network and we can do whatever we want. It's a lot of work, but works. But the question is, okay, but how well does it work? What can we get in the end? So first, we tested a very simple data sets because the data sets itself are not important. So we used MNIST, we used DPA-V4. DPA-V4 is a commonly used data set in sidechannel analysis domain. And then we trained a model and we did our attack, and we obtained the accuracy of 60.9%. So original neural network, 60.9% precision accuracy. Then what did we do? Well, we did the attack on that neural network and reconstructed it, reverse engineered it. We used that reverse engineered neural network, and we again did experiments with the DPA-V4 dataset. What did we get? Accuracy of 60.87%. So the difference between what we can reconstruct and what was the original in the performance is on the second decimal place. Why do we have that difference? Well, because we said we kind of reconstruct up to a certain precision. If there is an error, we will see a small error. Similar for MNIST. So the original one, 98.16%, reversed 98.15%. So average weight error was basically converging to 0.0025. So extremely small error per every weight. And then one would say, fine, this is multilayer perceptron, but can we do something more serious, something more exciting, like convolutional neural network? And we also did experiments there. We used Cypher-10 dataset. It's a common dataset in machine learning domain. Some small differences here for attack on CNN because we need to do operations using fixed point arithmetics. I will not bother you now with details. What's important to say, the original performance 78.47%, what we reconstruct 78.11. Actually, well, the difference is still very, very small, but we can see attacking CNNs is very difficult compared to attacking multilayer perceptrons. And what's even more, these are the correlations. So again, black one correct, red one wrong. And here you can see what does it mean having similar correlations for your correct and wrong guesses. And we actually see that we need to have up to 100,000 measurements to actually break something. And don't be fooled. To get 100,000 measurements from a small embedded device running convolutional neural network, that will take some time, and then obtain the measurements. The process itself is long, long, long. So finally, just to conclude, what's cool? Well, if we use relatively simple side channel techniques, so nothing fancy, nothing that we needed to invent, so all known stuff known for 20 plus years, we can break the neural network architecture in a way that we can reconstruct its behavior. What's very nice, well, this will actually scale linearly to the size of neural network. So the bigger the network, the more effort, but only linearly more. And finally, this is the first ever, maybe ever, let's say it like that, generic attack in nature, and actually more powerful because of that than previous attacks that went into this direction. So what's the point? What's the morale of the whole story? people are using machine learning in security applications, in any kind of applications. For many applications, we do not care what's happening with our machine learning. Who cares? You want my model, here you go. No one cares about the security. But there are applications where we do care about the security of our machine learning models. And in those settings, actually, if you use appropriate techniques, and if you are, let's say, limited power attacker, you can still reverse engineer the full neural network architecture, which says actually this is a domain that is open for future, because we will be needing many defenses that are actually cheap, especially for embedded devices, but strong enough to secure the device itself. And that would be all from my side. I think I'm exactly on time. Amazing.
Good job, Stjepan.
Yes. Let me see the questions, if there are questions. So first stop share. Oh, wow, so many. How doable is this against a GPU? Well, it's doable. The same concept, so now we are doing experiments with GPU, it's doable. What is the important message to say is that in the same way, like someone can use sidechannel to break AES that's running on GPU, you can use sidechannel for reverse engineering machine learning architecture that's running on GPU. What is a problem? Well, the problem is GPU is much more noisy, so the attack will be much more difficult from that side. What is advantage? Well, GPU is much faster than those ARM Cortex-M3 or whatever. So you will be able to run many more experiments in the same amount of time. I noticed that the tests were done on small microcontrollers. Have you ever tried this attack on any GPU device such as NVIDIA Tegra? So we are playing with that now, and like we said, it's possible. It's tricky. There are also some special problems, you know, if you have something like really fancy GPU that spends a lot of power, that also means it needs a lot of cooling, and then we need still to decapsulate to get some better signals. So how do we do that? It's kind of tricky and more complicated than for microcontrollers, but it's still doable. It's an effort, but no way that it's impossible. As the neural nets and weight sets grow, how does the attack scale given the amount of hypotheses you have to try? So we scale linearly in the number of elements we need to test. And of course, it's always a game for you to decide how precise do you want to be. Think of this scenario. Let's say my neural network weights are not floating points, but they are just integers between 1 and 100. Okay, then that means I have only 100 hypotheses to test. Well, if you say it's numbers between 1 and 1 million, well, you have a million hypotheses to test. So it also depends how precise you want to be. So do you want to look at 2 decimal places, 3 decimal places, or 10 decimal places? The more precision you want, the more hypotheses you need to test. So the model couldn't be used for reverse engineering the human brain. Well, we could encapsulate the human brain, but probably we would not go far with that and would not be very legal. So I would not recommend. Which CNN architecture and dataset are used for experiments? So for datasets, we used Cypher10, MNIST, classical machine learning datasets, and DPA-V4, classical sidechannel dataset for, well, usually for sidechannel analysis with machine learning. CNN architectures, well, various ones that we found online used. So for multilayer perceptrons, 4, 5, 10 hidden layers, a number of neurons. For CNNs, something like LeNet. From the architecture perspective and the attack perspective, there are no limitations, except you need architecture small enough to fit in the device like we had, microcontroller or ARM Cortex. So you will be very difficult to run something like ResNet at Mega. How would the difficulty of this attack change if the neural network uses 16-bit half precision floating point arithmetic? So if it's half 16-bit floating point arithmetic, you would have less hypothesis. So actually, your attack would be faster in that way. I'm not sure, do we just consider 16 bits or 16 bits is enough to show the weights? If we consider 16 bits, then performance of the attack would go down if the neural network still uses the full precision, but we just say we don't care. But if the neural network would only use 16 bits, it would just make the attack faster. If so, how many more traces did you find it takes? Well, like I said, it all depends on the target. If you attack something simple, couple of hundred traces enough. If you attack something complicated, hundreds of thousands of traces, depending on the setting, depending also on the quality of the equipment. So for instance, we used high quality EM probes, we used top equipment. So let's say that also helped us. If we did not have something like this, I'm not really optimistic about the effort one would need to have. Have you used any tools such as Chip Whisperer for probing? No. Chip Whisperer is a cool tool, very cool tool, but for something like this, we aim to go with some let's say, more expensive, more high quality equipment to get better signal to noise ratio. In essence, later in the breakout room, my co-author will be there, so maybe he will correct me. But in essence, I think one could use something like this, but would need so many traces that would say, well, the attack becomes much less practical because you would need so many measurements to fight against the wrong hypothesis. Have you tried attacking on RNNs? No. Why? Because we did not really know how to deal with the recurrency. So the question is how to deal with the recurrency while orchestrating the attack. Honestly, we do not know. We have some ideas. We tried some stuff, and we think it's possible. But at this point, I would really not be able to say how to deal with the recurrency. Did you think about applying machine learning on the side channel traces to overcome the noise? Oh, I'm not sure I understand the question. Well, yes, one could use machine learning on side channel traces to remove the noise. And this is something we did with more recently some other works. For instance, we used autoencoders to remove the noise. But we did not use that approach here because, like I said, we attacked the targets that were quite nice from the noise perspective, so we did not need more pre-processing. How to locate to the trace part that is related to the neural network processing? Well, you need to do some campaigns, you need to do some experiments to find the correct parts of the chip that are really used for the neural network processing. So experience and a lot of trial and error perspective. Which side channel helps much in your experiment in terms of easiness and accuracy, EM or power? So EM is better because it's more localized. So depends on your probe, but if you have very fine probe, so very precise probe, you can have very localized signal. If you have very localized signal, it will help tremendously to get a better signal to noise ratio, and then you will get cleaner signal, and then you will need much less measurements to break something. So EM would be better, but power would be cheaper. And that's all from the questions, it seems. Any mitigations or countermeasures you suggest? Well, there are papers that appeared after ours, and they said, well, you could use this, you could use that. There are always countermeasures. So this is the game that never ends. For any kind of attack, you can make a countermeasure, and then new attack for that countermeasure, whatever. The problem is not about devising a countermeasure. For instance, you could use classical countermeasures one would have one does for cryptographic devices. So something like hiding or masking. For instance, you could shuffle the order of your operations, and then it will be much more difficult to attack with this. The problem is always that trade-off between how much are you willing to spend on your countermeasure. because every countermeasure will take something. And then, especially if we are talking about embedded constrained devices like here, the big question is, can you afford it? Can you really spend so many resources to become more secure? I think this is the game that will change in future, and people will think more and more, yes, we need to spend resources to be secure, but currently most of the deployed stuff have no security. Do you think photon emission images from the activity of transistors can help more to extract details of neural networks? I presume so. I honestly do not know. Let's leave that for breakout room. My colleague Shivam, maybe he will know answer to this. I would say probably yes, but since I did not try it, I would not be comfortable saying really yes. Paper link, please. Sure. I need to go on Google and find it. It's called MaskNet. Wait. MaskNet. I think it's the one. Yes. So maybe there are newer versions of this paper, but I think this is the one.
Stjepan, I think we are out of time, but I have one last question before we move to the discussion room and the coffee break. How did you manage to schedule your talk for the exact time and your Q&A for 10 minutes exact time? How did you do that?
Lucky guess. It's like when you do side channel and from time to time you have a lucky guess. This was the same setting.
Okay, it was beautifully tested, and yeah, thank you so much for the amazing talk. Guys, we move you now to the breakout room, and if you have more questions, please interact with Stjepan over there.